Hello guys and welcome to this lesson. In this lesson we're going to talk about activity and half-life. Activity and half-life. There's a separate lesson on activity and the decay law. Is that okay? But here is just an overview on activity and half-life and also the relations we need in calculations involving activity or half-life. Is that okay? Now when you say activity, what is activity? So I've drafted some basic information over here on the board. When you say activity, it is simply the number of disintegration per unit time. Activity is the number of disintegration per unit time. So activity is the number of disintegrations per unit time, or we can say the rate of decay, the rate at which a radioactive material decays. That is activity. And this activity is directly proportional to the initial quantity of the radioactive material. We'll be going into detail on the lesson on activity and the decay law. Is that okay? So over here, just an overview. So activity is the number of disintegrations per time. Activity is measured using what we call the Geiger muller counter. Activity is measured using what we call the Geiger muller counter. Is that okay? That is activity. Now I want to talk about half-life. Half-life, it is represented by T half. Is that okay? T, small t, and then you put half on top of it. That is half-life. What is half-life? It is the time taken for half. It is the time taken for half of the initial amount of a radioactive element to decay. The time taken for half of the initial amount of a radioactive element to decay. The time taken for half of the initial amount of a radioactive element to decay. That time is known as half-life. Is that okay? That time is known as half-life. So for example, let's take for example that I have a radioactive material which has a mass of 100 grams. Is that okay? So the time taken for this radioactive material to disintegrate to half of itself. So half of 100 is what? Half of 100 is 50 grams. The time taken for this radioactive element to change to 50, that is half-life. That time it's used to break down from 100 to 50 is the half-life. And that is represented by T half. So if 50 also breaks down into 2, that is 25, we have another half-life. So this is the first half-life, this will be the second half-life. So half-life is simply the time taken or the duration for a radioactive material to decay into half of its original amount. Is that okay? And half-life also forms part of the factors that affect the stability of a nuclide. We said factors that affect the stability of a nuclide, we have one, we have the neutron to proton ratio, there is a lesson on that. We have two, the binding energy per nucleon, there is also a lesson on that. And also we have half-life. Is that okay? Now let's proceed. So in addition to those points, I also gave a point that the shorter the half-life, the faster the substance decay and the more unstable it is. So the shorter the half-life, if the substance decay half of its original amount, it means that that substance is unstable. So it's undergoing quick half-lives. Is that okay? So the shorter the half-life, the faster the substance undergoes decay and the more unstable the nuclide or the element. Is that okay? Alright, so I just gave some mathematical ideology here. I said at half-life, N naught is equal to, at half-life N is equal to N naught over 2. At half-life, N is equal to N naught over 2. And T is equal to T half. It simply means that at half-life, N naught we see over here is the initial amount of the radioactive element. Is that okay? So at half-life, this initial amount will be divided by 2. And that is the N. N is the final amount of the radioactive element. And the time, that is the T, which takes place when the N naught divides into 2, is the T half, and that is what? the half-life. Is that okay? So activity is the number of disintegrations per unit time, and it is measured using the Geiger muller counter. And also half-life is just the time taken for a radioactive element to disintegrate or decay by half of its initial amount or original amount. Is that okay? That is activity and half-life. And also in addition, I said that the shorter the half-life, the faster the substance decay and the more unstable it is. The shorter the half-life, the faster the substance undergoes decay or it breaks down. And it also suggests that the substance is unstable. That is why it is undergoing decay. Because radioactive elements undergoes decay due to instability. Is that okay? Very good. Alright, so the next aspect of this lesson is to know the relations we need once we're talking about calculations and the half-life. The relations we need once we're talking about calculations and the half-life. So I have written here relations used in half-life or activity calculations. The relations we need to use when we have questions on half-life and activities involving calculations. The first one I have here, half-life, T half is equal to ln 2 over K. T half is equal to ln 2 over K. So ln is on a calculator, you can put it on a calculator. So ln 2 is equal to 0.693 per approximation. So ln 2 here can be equal to 0.693. So it means that T half can be equal to 0.693 over K. We need to know this first relation. There is a lesson on this, on how to prove why T half is equal to ln 2 over K. Is that okay? Very good. Where K is equal to the decay constant. So K is a constant. Is that okay? K is a constant. So there is a variation between half-life, ln 2, and then K. T half is equal to ln 2 on K. So we can also make the decay constant the subject. Making the decay constant the subject becomes what? Ln 2 over T half. So we can get K to be equal to ln 2 over T half as well. Is that okay? So we can alternate between them. If we are given the half-life and we are asked to calculate for K, we just make K the subject. We can just punch ln 2 on the calculator. We're going to get 0.693 per approximation to 3 places of decimals. Is that okay? Very good. Another relation we need to know is ln into brackets n over n naught is equal to minus kt. Ln, so let me write it more. Ln of n over n naught is equal to kt. So ln is on the calculator that you can easily punch, and then we have n. N here represents the final amount of the radioactive material. The final amount of the radioactive material. And then N naught here represents the initial amount of the radioactive material. Is that okay? And then K here is the decay constant. And then T is the time taken for the radioactive element to undergo decay. The time taken for the radioactive element to undergo decay. Is that okay? So N is the final amount. N naught is the initial amount, K is the decay constant, and then T is the time taken. Is that okay? We can alternate between this. So we can also have ln of this time around N naught over N, and it's equal to what? KT. If it is N over N naught, it becomes minus KT. But if it is N naught over N, it becomes KT. Is that okay? Alright. Another relation we can also use, that is, we can eliminate the ln here by taking the ln inverse. Is that okay? Once you take the ln inverse, you're going to get n over n naught. That is when you're using this relation. The second one, n over n naught is equal to e raised to the exponent negative kt. You are using this one. So once you punch shift and then ln on the calculator, you get the e. Is that okay? The base. Alright, we can still use the same ideology for this one as well. You take the ln inverse, that is shift plus ln. You get n over n naught is equal to e, this time around, exponent kt. Is that okay? These are the basic relations we need in our half-life calculations. With this relations, we can solve all calculation questions on half-life without any further confusions. Is that okay? So we are going to take some examples of questions on half-life and the right relation to use in our calculation. Is that okay? All right.